Hey, this is a video for 9.5, Global Climate Change. So go ahead and check out the overview and set up your guided notes. So throughout Earth's history, there have been cyclical alterations to the climate, and that is due in particular to the Milankovitch cycles. We have changes to the obliquity, in other words, how the Earth is on the axis. And we also have changes in eccentricity, or the shape of the orbit around the sun. This means sometimes the Earth may be closer to or farther away from the sun. Sometimes the Earth may be angled slightly towards or away from the sun. And this will help to predict the climate tendencies or the climate norms throughout a given period. Now, other things that scientists have done is they've collected data and they've basically compared the data that they've collected in the past with what we currently know. So we've analyzed ocean sediments from the benthic regions at the bottom of the ocean. And in these sediments, we find organisms like foraminifera. Foraminifera are small little zooplankton. They have calcium carbonate shells. And what we will do is we will compare to find out which foraminifera or which zooplankton were present at certain points throughout our history. And what happens is these sediments line up on top of each other. And scientists have found out that at certain layers, there are certain organisms that have a particular range of tolerance. So for example, all of the organisms that are found at one particular level are found when the temperature is at a particular level as well. So we know this because we can compare it to organisms that are alive today. So each of these organisms have a particular range of tolerance, which means if, organism X is found at this layer, then we would compare it, we can, make an assumption based on organisms that are alive today and their ranges of tolerance. We would analyze this data and then we would formulate a hypothesis. But we also need to get other information. So scientists collect ice cores, basically taking a giant drill to Antarctica where the ice is, about a mile thick. And that's a lot of data from many, many, many thousand years. So they will pull this up and they might have 500,000 years worth of data. This is an example of a mock-up of one at the Museum of Natural History. But we would obtain the ice core samples and they would analyze the gases that are present in the air bubbles. So there's going to be some air bubbles present, every, several years, like a tiny, it doesn't rain, it doesn't snow, it's basically a desert in Antarctica, but there's going to be layers of ice that will build up throughout the year. So bubbles do get caught in there. And inside the bubbles, there's going to be different isotopes. For example, oxygen-16 and oxygen-18 are two naturally occurring isotopes. But oxygen-18 means it forms or it is present in higher quantities when the temperatures are higher. So if there are more oxygen-18 bubbles, they would assume that or hypothesize that the temperature was higher globally during that time. So they would compare that data with the samples from the ocean floor, and they would formulate some hypothesis regarding global temperatures. And what they have come up with is they have looked at the CO2 concentrations throughout, the last several 100,000 years, almost going back 1,000,000 years. And you'll see that there are peaks and valleys in this data. And then there is a giant peak because we are we have gone way up in our carbon dioxide levels. So this is unlike anything that has been seen. Now, some people might argue that this is, this might just be part of the Milankovitch cycles. Well, they've also looked at the temperature data, and this is what they have obtained from the ocean sediments and from the ice cores. So they can make predictions about the temperature. And if you notice, the temperature peaks and the carbon dioxide peaks are, pretty on point. The only problem is, the temperature peak is not as high right now. In fact, it should not be this high. Carbon dioxide is much higher currently than we have seen over the last million years. So this is a question of correlation or causation. They are definitely correlated. When we have high levels of carbon dioxide, we also have high temperatures. But what scientists cannot yet prove is that it is caused by the higher carbon dioxide levels. I mean, most scientists do agree that it is caused by this, but we cannot prove it to the skeptics, unfortunately. Now, what does this mean? Well, normally our atmospheric circulation, these patterns have been, we've had these patterns going for, many, many millennia. And this is because of the action of the Hadley cells. So the Hadley cells extend between 30 north and 30 south. But with climate change, the Hadley cells may expand because the temperatures will be warmer. It might have to go farther before it cools down, and those air currents fall back down to the earth. So normally our jet stream, is it's an atmospheric circulation high up in the atmosphere, and this is causing movement. It's basically like a river of air, and this is causing it's moving from west towards the east, and this is helping to form our weather patterns. However, with climate change, there may be a disruption to this. The jet stream may it may not be as smooth as it has been in the past, and it may rise way up into the Arctic regions and fall down into the tropics. Now, this could be a real problem when you have areas that are not used to being, like in winter, it might not be, might not be used to it being this cold at certain point. Areas out west, it might be much hotter than they are used to. So the global climate change doesn't mean that it's getting warmer. It means that the weather patterns are shifting. Climate patterns are shifting. I mean, this year alone, we've seen so many different rain events where we've had 2, maybe 3 inches of rain in 24 hours. And that I just don't remember that happening all that often, and it's been happening a lot in the past year. It's probably going to get a lot worse before it gets better. So we also have issues with the thermohaline circulation. So we'll talk more about this in the next video, but thermohaline circulation is the movement of water currents in the ocean. And in the North Atlantic, the water is coming from Greenland, it is melting, and then it is causing a buildup of fresh water. So with the glaciers that are melting on land in Greenland, it is building up in the North Atlantic, and that is preventing the water from sinking because it is less dense, the fresh water. So this is going to affect the Gulf Stream water, and it is going to actually cause cooling to Northern Europe because some of these water currents are not going to be flowing because there is not going to be as big of a difference in temperature to really drive this circulation. Now, there's going to be some impacts on barrier islands. Barrier islands are, like for example, the Rockaways are a barrier island. Coney Island is a barrier island. It's a skinny little landmass that just sits off of the mainland. This barrier island, this is Caye Caulker off the coast of Belize. This is where I was spending my spring break a few years ago. And what's happening is these barrier islands are not going to be able to withstand major storm events. And in fact, this is what happened. This was actually all connected. And then I think it was in the 1960s, there was a big storm that came through and basically just washed a channel, splitting this barrier island in half. Now it's actually called The Split. And it's a major tourist attraction. But these events are going to be far more common in future storm events. Another impact to the coastlines is the necessity of seawalls. So in areas that are really susceptible to erosion, or coastal flooding, seawalls may need to be constructed. We saw the impact of storm surges during Hurricane Sandy. New Orleans saw that during Hurricane Katrina. Hurricanes are going to become far more common in these upper latitudes where we live. And we may need to consider constructing some sort of seawall or some sort of flood protection or storm surge protection in the future. Now, the soil is going to be less viable because evaporation is going to happen at a much faster rate. And the really funny thing about soil is dry soil doesn't absorb water. So there's going to be much more erosion when we do get rain events. So it's going to evaporate faster and it is going to erode faster. This is the impact to the hydrology of various ecosystems that are affected by climate change. We're also going to have impacts in our polar regions, especially in the Arctic. The Arctic doesn't actually have any land masses. We have northern Greenland, but really at the North Pole, it is the Arctic Ocean, and it is usually covered by sea ice, but now the sea ice is exposing a lot of the ocean at different parts of the year. So this is a positive feedback loop because melting the polar ice is going to expose ocean waters, which has a very low albedo, and it's going to warm that water up. That warm water is then going to melt more ice. Again, because the less albedo, because there's less ice present, then it's going to expose more ocean water. Then it's going to warm more ocean water and melt more polar ice. This is just going to keep continuing and continuing. We will also see this in areas that have permafrost. So the permafrost will begin to melt. That will release methane. Because there is going to be decomposition when this permafrost is melting, the decomposition will be anaerobic decomposition, releasing methane. That methane has a high warming potential. It's going to increase the atmospheric temperatures. So the permafrost is then going to melt more, releasing more methane, warming the atmosphere, melting even more permafrost. So this is an illustration or an animation of the sea ice. You'll see it building and shrinking during the summer months and the winter months. This has been between 2013 and 2016, which was, kind of an interesting time because the sea ice was retreating more than it has in the past. So a couple of things you notice is you actually have shipping routes now. You could probably ship between parts of northern Russia and parts of northern Europe, and you don't have to go on land, and you can actually, there might be shipping channels that are available and opening up through the Arctic Ocean. This is actually a benefit, a human benefit. It's not the kind of benefit that we really want. Another thing is these polar bears are used to living on the sea ice, and some of them will live on the sea ice year round. But when the sea ice is broken up, you'll see polar bears entering human areas, so there may be a lot more competition. And when polar bears are interfering with human life, there might be a higher chance that they will get shot. And polar bears are already vulnerable organisms, and we don't want them to become extinct, which their habitat is already being destroyed. So any opportunity to protect them is better than just killing them on sight. So what I would like you to do, there was a lot of information here, but I would like you to respond to this check for understanding. And for FRQ practice, I want you to describe a positive feedback loop that's associated with global climate change. I hope that this video is informative. I thank you for your attention, and I will see you soon.